Before that one, you saw the rockets going up there, coming back down and landing. And they could reuse it again for the next cycle, right? That's pretty cool if you think about it, right? Imagine that conversation in that room saying, why do we need to throw away the rocket, right? Somebody on their side saying, what's the alternative, right? Well, we can land it, and somebody, I'm sure, was like, you're crazy, there's no way we can do that, right? But that curiosity, right, and challenging the norm, and look at where we are now. You could say the same thing about electric vehicles, right? I mean, electric vehicles, decades ago, there was an idea, kind of died away, but then all of a sudden now that's coming again, right? And think about not only the electric vehicles, but think about the features that continue to be added to cars to make them safer. Nowadays you have cars that can detect if something is in front of you and give you an alarm, or actually even brake for you, right? Even something as simple as the blind spot monitoring. Years ago, a lot of accidents because you couldn't see who was next to you, right? Now vehicles can give you an alarm and give you a warning and try to avoid that, right? So challenging the reason why and staying curious is one of the things that drive innovation. And as you go out there, by your careers, ask questions. Stay curious. Ask a lot about the why. As I went through my role as a test engineer, I continued with that curiosity, started asking questions, and then I started really trying to understand why do we add certain features to the devices. And really, that curiosity then led me to, I want to learn more about what problems the customers are trying to solve. That's when I decided to shift my focus from test engineering into systems, product definition, and product line leadership. It was really about, I want to understand what are the problems the customers are facing and what I can do, or my team can do. And the fact of the matter is, everything that we talked about here, be it, safety, be it, landing a rocket and all that kind of stuff, these are very, very, very difficult problems, right? So the other thing that I would tell you as you go into your professional world is have a make it happen mentality. What does that mean, right? Again, problems are going to be difficult and you are going to face a lot of challenges, right? What I look for in people in my team is people that have that maniacal focus on getting things done, right? And trying things, making mistakes, learning from them. There was a very famous inventor, you probably have heard this quote, he said, I have not failed, I have just found 10,000 ways that it won't work. Anybody knows who said that? Thomas Edison. That's right, Thomas Edison. And when you hear that, right, it's actually pretty cool, and that's really the essence of making it happen, right? Understanding, how to go drive problems. In my mind, when I hear that quote, there's two things that come to mind. The first one is the obvious one, right? Which is 10,000 ways I fail, right? Or that it won't work. That really speaks to you learn from making mistakes, right? When you do something and it doesn't work, you learn that that's not the way to do it, right? And when I think about things that we have seen from customers or even myself in my career, we were actually once, a few years ago, we were trying to integrate a transformer into an IC. We're talking about 8 millimeter wide, 2 millimeter height, and being able to transmit half a watt of power with about a 10,000 volt isolation. And we were looking at that, it's like, this is extremely difficult for us to be able to do. But we went ahead and started building it. And the first parts that we built did not work. It was not manufacturable or anything. So we learned what not to do. But from there, we fed what we should be doing in order for us to be able to fix it, right? So having that make it happen mentality is very, very important. The second point that that in my mind comes out of that quote is about ownership, right? He talks about, I have learned, not, they have learned or somebody else have learned. I have learned 10,000 ways that it won't work. And that ownership is extremely important as well. One of the things that I always tell my team is, when there is a problem, something goes wrong, I want you to find a way to point back right at you, meaning it didn't work because of this. This is what I could have done differently. And the reason I say that is the moment you make it your problem, then now you have a motivation to go ahead and solve it. I always, when we get into reviews with my team, I tell them, when there is something going wrong, I want that thorn, la espina, I want that thorn to be right on my side. Why? Because when that thorn is in you, you're gonna pick at it until you can get it out, right? It bugs you, it hurts you, right? So that's really what ownership is about, and that's why when you go out there, you're working on something. You're gonna be working on a team environment. Something goes wrong. Think about what you could have done for the team and what you could have done differently as a team to get this thing moving forward. Learn from those mistakes, right, and find different ways to get things solved. I want to be very clear on that point. When you go out there, you're going to make mistakes. I've made plenty of mistakes in my career. It's all about what you build on those and what you learn from those. That sets you apart. This leads me to the last point I want to make, and something that I also want you to think about as you go out in the world. We just talked about mistakes and learning from those mistakes. The next one is continuous improvement. Have a mentality of continuous improvement. What does that mean? Well, we just talked about learning from the mistakes, but can you also learn from your success? And the answer is yes. If something goes really well, there's absolutely a lot you can learn from that, and absolutely a way to make it even better. One of the things that I always talk about with my team is, hey, we did something good, how do we make it great? And if you always have that mentality of going from good to great, it's just going to continue to feed you. It's going to continue to drive that energy to go ahead and find the next big challenge. I'll give you one more example I had. This was probably 8 or 9 years ago. We were trying to come up with a solution for driving the motor of an electric vehicle. And we were looking at a lot of competing technologies, IGBT, silicon carbide. And we wanted to come out with a solution that could intersect the market, but also make it easier for our customers to implement that solution. So the team got together, we came up with a proposal, we released that product, we put it on the market, and that part had a lot of success. A lot of customers designing it in, a lot of customers using it on their cars, on their prototypes, and all that kind of stuff. And I got the team together and we talked about, so I asked a simple question, which was like, this is an awesome product, this is really good. What we could have done better? And there were a long list of things that we learned from that, right? It was like, hey, you know what, we could have done this on the output stage to make it easier to tackle EMI problems, or we could have had this feature to protect under these conditions and all of that. And that's what you're looking for, right? Because now that feeds what your next generation looks like. And quite frankly, the people that you work with feed off of that, right? Because you have that, focus and just continue to get better and better. In the business world, we have a lot of metrics that we look at. And I always tell my team, guess what happens when we have a green scorecard across the board? That bar goes higher. I'm not looking for a green scorecard. I want that bar to continue to go up so that we can continue to get better and better, right? Again, going from good to great. So in summary, what I would say as you go into your professional careers, number one, stay curious. Ask a lot of questions, challenge the norm, challenge where we're going, challenge what technology should be doing. Have a make it happen mentality. Go drive, don't take what is given, just make sure you get to where you want to go. Learn from those mistakes, be accountable, take that ownership when things go right, take that ownership when things go wrong, and drive towards a better place. And last but not least, have that mentality of continuous improvement, right? Anything that is good can always be great. So if you have that mentality, you're going to be successful as you go out there. So again, thank you for giving me the opportunity to speak to you today, and really looking forward to the presentations today. I did see the list of projects, and there's some pretty cool stuff out there. So really looking forward to the presentations, and more importantly, really looking forward to seeing you all as you go into your professional careers, and really how you continue to drive technology, whatever you are, moving forward. So thank you.
quick question.
Yes.
Throughout your career, probably you went through different stages and different people where you were under. How did you deal with difficult situations with your supervisors or managers?
I know who you're talking about. It's a good question. The fact of the matter is, when you go out there, you're gonna find good managers and bad managers. That's the reality. And really, bring it back. What I always did was bring it back to what are the results that we need to get to, and drive towards those results. It takes patience. It takes a lot of courage. But you're gonna find that even in college, when you're on a team project, you're gonna have people that perhaps you and them don't quite jive, right? So figuring out will just make you stronger. And quite frankly, at the end of the day, if you cannot find a good person to work with, find a different job. There's gonna be opportunities, and that's the beauty of big companies. You have a lot of opportunities to move along as well.
Thank you.
And again, I know who you're talking about.
It wasn't
Yes.
a question, it was a jab.
Yes.
En español también.
Puede ser en español.
Yo entendí algo ahí que dijiste que no le echen tanto la culpa a los estudiantes a los profesores.
Exacto. Si sacaste una F, mira a ver que tú pudiste haber hecho distinto.
You mentioned about innovation,
Yes.
and you talk about the relation about intellectual property, how you protect that, and how you interact, the engineering and the lawyers, how you achieve that kind of protection of patents and so on.
Good question. Obviously, different companies treat it differently. I can tell you specifically on Texas Instruments, we have a big team of lawyers focused on IP protection and patents. So as you're working on new projects, you come up with an idea, go ahead, you write that form, you get it to our lawyers, they'll meet with you, and we'll get that protected for TI as well, right? And obviously you get a cash bonus as part of that process as well. But it is very important, right? I mean, the fact of the matter is, everything that we just talked about, there's patents and ideas that come out of there. And some of them are great, some of them are not so great. But the fact of the matter is, as you're thinking about what's different, how you're solving a problem differently, make sure you submit that, right? And most companies will have that process to help you actually submit those as well, and not only get them submitted, but file and protect it for you and for the company. Does that answer your question, Professor? No hay problema.
¿Cómo fue tu empeño académico para después entrar al laboral? Cuando te graduaste, ¿cómo fue que hiciste para poder entrar en ese lado, ser competitivo en el lado académico para después llegar al profesional?
So, cuando yo estuve aquí en el colegio, mi enfoque fue en electrónica. Tomé muchas clases de electrónica. Pero en mi opinión, lo más que me ayudó fueron dos cosas. Número uno, hacer el internado. Hice un co-op con TI, hice un summer internship con TI. Tuve un verano que me fui a la Universidad de Purdue, hice un summer research con la Universidad de Purdue as well. Y lo otro que me ayudó fue proyectos como el de IAP. O sea, si tú te das cuenta, muchas veces todos los estudiantes van a tener su bachillerato, van a pasar lo que se gradúan, terminan con su bachillerato. Como tú diferencias, como tú stands out, ¿qué tú has hecho en adicional a tu clase? Cuando tú buscas, por ejemplo, compañías como TI, nosotros buscamos un GPA de 3.0 para arriba. Y eso es como que el first step. Una vez tú tienes ese 3.0, entonces estamos buscando qué tú has hecho. Todo el mundo tomó la clase de circuitos 1, circuitos 2, electrónica, pero qué tú has hecho aparte de eso es lo que te ayuda. En verdad, la universidad del colegio, la educación es tremenda. Cuando nosotros fuimos aquí está Modesto, él es parte del Mayagüez. Nosotros tenemos, él es director de operaciones también en Texas Instruments. Tenemos gente que son distinguished members of the technical staff, que es un ladder que tenemos para gente que no se quieren enfocar en business, se quieren enfocar en technical contributions. Tenemos estudiantes que se han graduado de aquí, que tienen sobre 30 patentes ahora mismo en TI y todos los días siguen sometiendo nuevas patentes. So, lo que nos ayudó fue simplemente lo que aprendimos, llevarlos allá y entonces aplicarlo. Y eso es lo que te da el research, eso es lo que te da los internados, oportunidades de aplicar lo que ya has aprendido. Build on this.
Your first experience adding to your resume was the TI internship?
No, actually, my first one was my summer research in Purdue, and then right after that, I did the co-op in TI.
So usually, but personally, I spent a lot of years trying to get involved, but it was a little hard for me because I wasn't as social, and I had trouble making connections. And I wanted to see how that experience was for you.
I'm very introvert, by the way.
Yeah.
Sí, yo súper callado, súper not very social. Pero honestamente lo que yo noté fue tuve que push myself outside of the comfort zone. That was the only way. Y me empujé para ir a hacer el research. Well, frankly, esa fue la primera vez que yo estuve fuera de Puerto Rico por meses. O sea, nunca lo había hecho anteriormente. Y hice mi research después, cuando hice mi co, fueron 6 meses que estuve fuera de Puerto Rico. Ayer yo hice una historia de que fui a un Walmart porque necesitaba ir a comprar algo y cuando fui a pedir lo que necesitaba no sabía ni cómo decirlo en inglés. Push yourself outside of that comfort zone.
Take the lead.
Take the lead. Y la realidad es que la educación otra vez de aquí del colegio es second to none, honestamente. So, the knowledge that you tienes cuando sales de aquí is really, really strong. So, you shouldn't feel afraid or scared or whatever. Just put yourself out there. Y honestamente, eso es lo que buscamos nosotros también.
Thank you.
Y déjeme hacer un comentario en el lado serio.
Solo micrófono, si puedes.
¿Tiene micrófono?
No, los micrófonos.
Ok.
Ok.
Para que se oiga fuera de
Sí,
estamos en vivo.
es que quería decirle una parte de lo que él está diciendo, porque tuve una experiencia reciente de un estudiante que me mostró un resumen y las cosas que está haciendo con ustedes ahora de IAP no estaban ahí. Porque ustedes a veces se creen que eso no es importante. Y él les acaba de decir que eso fue importante en su caso. No subestimen eso que ustedes están haciendo, que parece una tontería, pero no lo es. Es bien profundo. Ustedes tienen una base técnica importante con los cursos. Electrónica 1, electrónica 2, controles. Por ejemplo, controles en muchas universidades en Estados Unidos no existe como curso subgraduado. Y nosotros tenemos controles. Tenemos control digital. Y voy a hacer una pequeña anécdota también. Pero lo que les quiero decir es que ese trabajo que ustedes están haciendo de investigación subgraduada es bien valioso. Sabemos también que hay gente que lo pone, yo hago eso para ponerlo en resumen. No, pero no es eso nada más, es trabajar duro de verdad y entonces lo pones en resumen. Sacas un buen resultado y esa experiencia es importante. ¿Por qué no es ponerlo en resumen nada más? Porque un día te entrevistan y si no sabes, pues no quedaste bien, por no decir otra cosa. Yo tengo una anécdota, nosotros trabajamos con el C2000, C2000, el microcontroller, y un estudiante que ayudó al estudiante graduado a desarrollar eso, se entrevistó con General Motors, con los controles de motores eléctricos para los carros eléctricos de General Motors, y es el único estudiante puertorriqueño primero y segundo que tiene bachillerato en ese grupo de trabajo. ¿Por qué? Porque hizo ese trabajo con el C2000. Así que, para que vean que una cosita así chiquitita puede ser algo bien significativo. Todos los demás miembros de ese equipo de trabajo donde él está en General Motors tienen o maestría o doctorado. Es el único con bachillerato y puertorriqueño.
Lo que dijo el profesor es muy cierto. Yo he tenido oportunidades de ir a universidades a entrevistar. Y le voy a decir cuál es el truco mío de entrevista. Tú me das tu resumen, tú me dices qué tú enseñaste y yo te voy a preguntar de este proyecto que tú pusiste ahí. Es muy fácil ver quién hizo el trabajo y quién no lo hizo. Es bien fácil. Por eso cuando you get out what you put in. Cuando tú haces estos proyectos, trabájalo fuerte, aprende. Cuando tú vayas a esa entrevista, you're gonna knock it out of the park. Y eso, ese es mi truco. Yo estoy seguro que Mo utiliza lo mismo. I'm sure Raffle does the same thing. Looks like what's on your resume, ask about it, and then see how much you can talk about it as well, right? It's not a secret.
Seguiré buscando el control. Sí, les recuerdo para los que llegaron a última hora, tienen que señalar el micrófono hacia el frente, la antenita en la parte de abajo, usted pone la mano al frente o cerca de la antena, puede perder el sonido. Le pasó al compañero aquí unas cuantas veces, esa es la razón. Esperemos que no se agoten las baterías de aquí a la tarde. Okay. I will switch to English now because the conference should be in English. The next group will be variable command response type rotorcraft control system. Pueden empezar a que estoy seteando que se vea la presentación en el...
El live.
Good morning, my name is Christopher Leon. I'm with my colleague Colin Jimenez. Today we'll present our research project, Variable Command Response Type Rotorcraft Control System, sponsored by Lockheed Martin Corporation through the Industrial Affiliates Program. Our advisor professor is Dr. Gerson Buchamp, and our company liaison is Wilson Ronda. This is the outline of our presentation. In the introduction, I'll talk about the importance of helicopters and their capabilities, as well as present the problem, hypothesis, and the objectives of our project. Finally, Edwin will present the methodology, our accomplishments since last year, future work, and conclusion. Igor Sikorsky once said, "It would be right to say that the helicopter's role in saving lives represents one of the most glorious pages in the history of human flight." But why was it so glorious? By the year the helicopter was developed, there was no other aircraft as maneuverable as the helicopter. If we compare the wings of a helicopter and the wings of an airplane, we can say they are very different. The wings of an airplane are fixed and require the airplane to reach a minimum velocity to achieve lift. That is why they need a long runway to take off and land. On the other hand, the rotary wings of helicopters function differently. They achieve the threshold velocity by rotating around an axis, eliminating the need for a long runway. That is why helicopters can take off and land vertically, hover, and move towards any direction. Thanks to these capabilities, they are often used in many critical operations such as search and rescue, surveillance, firefighting, and transmission line maintenance. The problem we have is that helicopters are unstable systems that require an exhausting amount of work from the pilot. An automatic control system is required to accomplish flight stability and adequate performance. This system will allow the integration of different flight command modes that facilitate maneuverability and flight control. In the research project, we propose to design various flight command modes that will help stabilize the helicopter, regulate its performance, and accommodate operators of different skill levels by implementing advanced control system theory. These flight command modes will help a pilot control the aircraft, stabilize the rotorcraft, and keep both the pilot and the aircraft safe. The main objective is to develop and implement the control system in a Pixar microcontroller through autopilot. We will implement 4 flight modes. First, we have the altitude command altitude hold flight mode. This system stabilizes the helicopter and maintains its altitude, allowing the pilot to focus on controlling the aircraft's position. Second, we have the position command altitude hold flight mode. This flight mode stabilizes the helicopter and maintains its position when the pilot lets go of the controller. Then we have the velocity command flight mode. In this system, the engine's velocity is directly proportional to the commands given. This means that small commands will generate a small amount of velocity. Finally, the rate command altitude hold involves controlling the forward and side velocities using the aircraft cyclic control. The pilot controls the rate of motion instead of the position.
As part of our methodology, we first implemented the PSOC microcontroller in the helicopter with the AutoPilot open source software. In this stage, we ensured the system had the correct wiring, channel mappings, servo directions, and servo calibration. After all the pre-flight requirements were met, a test flight with the helicopter controlled by the PSOC and its default firmware was conducted. When this was completed, we proceeded to revise and analyze the autopilot code. As part of our accomplishment, we successfully implemented and tested 3 of the proposed flight modes, which are the stabilize, the altitude hold, and the position hold flight mode. We had a successful autonomous landing using the return to launch feature implemented on Mission Planner. Now we are ready to implement and test the rate command flight mode. Now we will see a video where we show the altitude flight mode. This mode controls the height of the helicopter so that it will stay the same. This means that the pilot can move freely, but the height of the helicopter will stay the same unless manually modified by the pilot.
Here the pilot turned on the flight mode and automatically the helicopter stayed at the same altitude. It was around 10.7 meters. Once he knew the flight mode was working correctly, then he flew freely. It's hard to tell, but the helicopter, it's maintained its altitude. This is one of the most easier flight modes for a novice pilot. And it requires little effort from the pilot because it's maintaining its altitude.
As part of our future work, we will install a new Cube pilot system to the RC helicopter and test the previous flight modes with it. The next step would be to implement and test the rate command altitude hold flight mode. When this is done, we would proceed to design velocity command altitude hold flight mode in autopilot code. Finally, we will study and analyze the helicopter's behavior while flying under the different flight modes to improve stability and control. In conclusion, we have set the path to start designing and implementing the velocity command flight mode. We have done correct wiring, channel mapping, servo directions, and sensor calibration to then proceed to the pre-arm and safety check. The helicopter is ready to arm and test flight. Finally, the autopilot and autocopter basic concept knowledge was acquired. That way, when we come back next semester, we are ready and more efficient at carrying out this investigation. We wish to thank Dr. Gerson Bouchamp for his guidance, commitment, and time devoted to the development of this project. We also thank our liaison, Wilson Ronda, for always believing in the talent at UPRM. Here are our references.
So I think I have one suggestion and one question. So suggestion is that it seems like you were, I think you guys did the project, right? And so you know your work. And I think it seems like you were reading rather than presenting.
Yep.
So next time, I think since you know your material, I would recommend try to, what's on the screen, summarize it rather than reading it. That's one thing. Second thing, I did not see technically what did you do in your project to make things happen. So that's maybe you can explain.
So what we did, we have a software program called Mission Planner. In that program, we have different flight modes available. And what we did was implement those flight modes in our helicopter and adjust the PID gains of each axis, because each flight mode has different controllers. Most of them have PID, others just have proportional controllers. But mainly what we just did is implement those flight modes in our helicopter, because the problem with Mission Planner is that most of these flight modes are designed for drones, not for helicopters. So we adjusted worked our way around and implemented those flight modes in our helicopter and adjusted the controller gains.
How did you deal with the velocity of the wind as you rise, or when it's in a steady mode? How does it deal with the different velocities of the wind and direction?
So with the wind and velocities, when it's in the altitude mode or the position hold or any of the modes, it has a gyroscope that would automatically readjust the axis so that if it goes to the left, it will compensate and go to the right and try to stay as stable as possible.
Thank you.
What was the most challenging aspect of the project?
Well, for me, it was that when we started working on this investigation, it was post-pandemic. So every bit of knowledge that was acquired before us, we didn't know. We had to start from the very beginning, reading everything, checking the manuals, the code, everything, and even how to calibrate the helicopter. That took us like a semester approximately. After that, it was pretty smooth, besides some troubleshooting and other problems that we had through the way. But mostly for me, it was acquiring that knowledge from scratch.
Thank you. Any other questions?
I had a question about the flight controller, because from my understanding is that you guys made a new mode for the FaceTalk. So my question is that code that you're reading somewhere else, or is that something you write or do in the FaceTalk?
The flight modes that we already have were already implemented on the Mission Planner or autopilot. The only mode that we're going to have to add with the open source is the velocity command flight mode, which we have a econ student who's going to help us with that. But the other three modes were already implemented. They're already integrated into the cube connected to the helicopter. So we just have to press a switch and it will automatically change.
change the parameters.
We also did, we changed some parameters inside the mission planner software. Some of the parameters weren't exactly made for the helicopters. That's why we had to adjust some of the parameters. But to answer your question, those flight modes, we didn't do them from scratch. The only one we're gonna do from scratch is the velocity.
What is the ultimate goal?
Our ultimate goal is to create autonomous flight modes, mostly fly the helicopter autonomously, as well as developing our own controller um, to fly the helicopter safely. We achieved autonomous landing. We did not achieve autonomous flight yet.
Are you planning on the design to be extensible to other types of vehicles, such as a drone, for example?
For now, we are only focusing on helicopters. No more questions.
Thank you. Very lovely, change of presentation. The next presentation is the solar boats. Solar boat, are you here? Yes.
Good morning, everyone. Thank you for being here. My name is Cindy Serrano, and today I'm accompanied by my teammate, Giancarlo Negro, and we will be talking about the UPR solar boat. So the UPR solar boat competes every year in a competition called the Solar Splash. This is an intercollegiate competition where universities across the United States compete in a solar boat electric competition. So to make it simple, we design, manufacture, and compete with a fully electric watercraft that we drive. This is a 5-day event where we compete in a total of 7 categories or events to accumulate a total of 1,000 points. So going into our overall scores, last year we were able to get second place. We got short to Cedar Hole University. We were able to come up with 898 points, and they were able to get 932 points. So we were able to see our biggest weakness last year. It was at the endurance event. That's where Cedar Hole University was able to get around 400 points, and we got 354 points. This was because during the endurance event, we had designed a propeller that we thought it was going to work for us better last year, and eventually didn't give the performance that we thought it was going to give. So that's one of the things that we're working on this year. Once again. So here's when we first saw that propeller was not giving us the performance that we expected it. This is the qualifying race is done with the endurance setting, so endurance batteries and endurance propeller. And this is when we first saw that we were not looking good in terms of endurance compared to other universities. So some speed goals. So obviously the team always wants to go a little bit faster because that's what helps you, get to your destination and get some extra points. So in terms of sprint speed, we have always been pretty good at that, and we've been able to keep making the boat faster. We are around 14 meters per second right now, which is around 30 miles per hour. And then in endurance speed, we are aiming at 3.6. As you can see, 3.6 meters per second was what we were looking for last year. But unfortunately, like I said, due to that propeller, we weren't able to do that. So that's what we're working on this year again. So in terms of our objectives as a team, we have designed 4 new propellers, or at least the mechanical division has designed 4 new endurance propellers so that we can test them in different types of aspects. Everything is done through MATLAB OpenProp, and we've also acquired a new thrust sensor that we've programmed into our data acquisition system. We also have a 24 volt to 36 volt switching circuitry, and we've also had a new solar panel array frame that we've changed from our materials from our past year. So in terms of solar system design, we have overland solar panels. Each panel has a total of 160 watts. That gives us a maximum of 480 watts, which is the maximum limit by the competition. So we're operating at the highest capability that we can in terms of, irradiance collection. And then the solar panels lay on a T-slot aluminum extrusion frame. We originally had carbon fiber tubes, but these tubes, they were pretty rigid, but in terms of the structure that we had them, putting them on and off the boat was a little bit hard, and then they were not very stable, so we ended up breaking some of them. So now we've decided to do T-slot aluminum extrusion frame. This is a little bit more rigid, and it's going to be easier for us to take it off and on, and hopefully it doesn't break in that process. So in terms of power electronics box improvement, so we originally had 2 types of controllers for speeds. We had high speeds, we had that big Kelly controller, and then for low speed, we had the little baby one on the right side. So this year, we've decided to only keep the big one for both high speeds and low speeds. And then on the right side, we took that small motor controller, and now we have that switching circuitry that's going to gives us either 24 volts or 36 volts when we want it. So hopefully you can kind of see that our system essentially has 4 batteries. We have 2 PC950s and 2 PC1100s. So when the switch is going to be open, we are going to have both sets of batteries in series, which will have them at 24 volts, and then those 2 will be in parallel, which will keep us at 24 volts. When we close the switch, what we're going to do is we're essentially limiting that bottom left battery, and we're going to have this 2 sets of batteries on the right in series, and then that'll be in series with the with the top left battery, which will give us around the 36 volts. Our batteries do charge a little bit more than 12 volts, so if you see like the data there, it says 25 and around 40 volts, that's because of that, because our batteries are not strictly 12 volts. And now Dan will take over everything mechanical.
Hello, I'm Giancarlo Negron. I'm part of the mechanical division of the solar boat team. So right now the mechanical division this semester is sort of focused on propeller design, trying to make more efficient propellers. In order to do that, we use a custom-made program in MATLAB, which allows us to measure the efficiency of and compare the efficiency of both the electrical systems and the propeller. So here we also use a program called se me fue el nombre. OpenProp, yes, that's called OpenProp. And we combined our custom-made MATLAB code with OpenProp in order to sort of make a more efficient workflow. So here we can see sort of like the design parameters and what we're looking for. Right now we're trying to maximize speed and efficiency. So in these charts here we can see 2 propeller designs for the endurance event. Just for further information, endurance event is an event in which we try to run the boat for as long as possible. which we do that through the collection of energy through solar panels and also the batteries that we have inside the boat. For that event, we want the propellers to be as efficient as possible, but also we want to maximize speed in that event as well in order to get the most amount of distance possible as well. So it's sort of balancing those two factors. So we have two propeller designs right here. Without chord optimization, that is another tool within OpenProp that allows the program to optimize the, it's kind of hard to show here, but it would be the width of the blade here. And then we also have two other propellers with chord optimization. And these are the four propellers that we are designing and that we have manufactured up till now, which should be more efficient than the propellers that we had before. So here we have efficiency graphs. In red, we have the efficiency of the motor that we're using to drive the propellers. In blue, we have the efficiency of the propeller itself. And in green, we have the efficiency of the system as a whole. And as we can see, like the system gains efficiency at the higher RPM ranges, which is where we designed the propellers to be. And then here are two graphs of the efficiency of the system as a whole versus RPM, which we can see again increases as we increase RPM. An important aspect of propeller design is analyzing the possibility of cavitation. If you don't know, cavitation is when it's a large problem within boating where the propeller goes so fast where it basically creates like these tiny vacuum bubbles behind the propeller. And these bubbles can collapse at extremely high pressures and heats, which damage the blade, cause excess drag, and lose efficiency on the blade. So this isn't something that the program takes into account when calculating efficiency. So it's something that we need to do ourselves with cavitation analysis, and this step is very important to make sure that we're not designing blades that will lose all their efficiency due to cavitation and we're not noticing. These are the four propellers manufactured. It's sort of important to note, you can't really get the scale here, but the boat is pretty big. Like this is a boat that 15 feet, so Sydney's able to ride it, and there's still like quite a bit of space, so it's a pretty big project. So this is our data acquisition system. So all the data from all the sensors end up coming here, and all the data is stored on an SD card, which is all acquired through this component right here. Now, through all of our sensors, we're able to measure the voltage and the current from the batteries. We're able to measure our speed relative to the water, and we're able to measure the RPM of the propeller and thrust, which the mechanical division was recently able to implement. So in order, it's quite a clever system thought up by our captain. In order to measure thrust, we use it's a sensor that actually measures like the distance of compression between the propeller and the body of the boat. So you may be thinking like, oh, if we're measuring how much is compressing, how are we measuring force? And we do that by measuring how much force does it take to compress a certain distance. And by taking that graph, we're able to measure the actual force output of the propeller. Thank you very much. The floor is now open for questions.
Yes. What kind of models are you using for cavitation analysis?
Right now we're using the built-in model in OpenProp. So if you're able to download that program, which is a simulation that goes into MATLAB, you can see the cavitation analysis program within there. Yeah.
Real good presentation, so good job. Question, you tried to get the engine speed to 3.6. Question is why 3.6 and where are you right now?
The reason for 3.6 meters per second would be, it's sort of like the optimal range between the power output that we can get out of the batteries, between the power that we're collecting from the solar panels, and the efficiency of the electrical systems plus the efficiency of the propeller itself. To sort of trying to match the efficiencies of all that system, we came up around 3.6 meters per second right now.
So essentially, the endurance event is a 2-hour event, right? And you have to do loops with your boat. 3.6 meters per second is what we're able to, through the data that we've got, understand that it's the number that the fastest that we can go without depleting our battery. So at 3.6 meters per second, at 2 hours, our batteries are like at 1%. So that way we can get the maximum of our batteries. What happens with other competitors is that sometimes they don't do this number, they don't do this analysis, and they'll go very fast, and they'll do maybe 10 loops, and then their batteries are dead. At 3.6 meters per second with the batteries that we have, that's the fastest that we can go without using the solar panels. So everything that we get from the solar panels is like a little extra bonus.
So what did you achieve last?
Last year we were around 3.2 instead of 3.6. Unfortunately, like we said, the propeller didn't give the performance that we wanted. So that's what we did for this year to test different propellers and take the best one over there.
You talked about the switching between 24 and 36. What's the thought process? What are you trying to get with that?
Okay, so for the endurance qualifier, you can be at 36 volts. And last year we did the endurance qualifier with 24 volt array of batteries, and our propeller performed at like 22 volts, so it didn't have any space for big performance. So that's where we were able to see that we were having a lot of problems with that propeller. So this year we're trying to do the endurance qualifier with 36 volts with a propeller that operates at 24, so it has room for going faster. Yeah.
Okay.
Yes.
Where was that propeller built, constructed?
So we outsource all of our propellers online to manufacturers in the U.S. And Asia. Unfortunately, we have some CNCs here, but we weren't able to do. Our manufacturing process was not as good as theirs. But yeah.
Can you tell me 3 things that you learned through this experience? The 3 most important things.
I think the biggest thing is patience. So while working with the boat, you tend to find a lot of little problems, and especially us, since we are a team that has to fly out with this. It's a 15-foot boat, so we have to fly out with a huge crate, and then everybody just like drives their boat to the lake, and we're building our boat in the lake. So those first like 2 or 3 days that we're there, it's very, I would say, stressful, and a lot of like small errors happen that takes a lot of time to fix. So sometimes we'll like break something, and then we're like spending 3 hours fixing that thing that we broke instead of finishing building the boat. So I think that's one of the biggest things. How about you?
One of the biggest things I learned was how long a lot of processes actually take, even though they may seem simple. So even and how many like small problems that you never would have even thought of come up. So it's very important to sort of keep that in mind when you're analyzing like your time frames for like deadlines and things like that. Where a lot of the processes that may seem simple is like, oh, we can do this pretty easily. It may take like 1 or 2 days, and now it's probably going to take like 2 weeks to try to do that and try to like sort of iron out all the kinks in the system.
And I think the third thing would be testing, the importance of testing. So last year, that's why we were unable to see the performance on our blade, on our propeller, because we got short in terms of testing, and we tested with our boat a lot of things, but the propellers that we outsourced didn't get to Puerto Rico on time. So maybe we should have given that like a little bit more lead time to get here. So we just sent our propellers to go higher where the competition is, and we were blindly trusting on the on the analysis that we had done. And then when we got there, that's when we saw like that it wasn't giving the performance that we wanted. So testing is a huge thing for sure. Hey, thank you.
Thank you for our vote. We have the President of the Chancellor with us. I will invite him to say a few words about IAP.
Okay, good morning, everyone. The detail here. Uh, Welcome, all of our visitors to our Maya West Campus. Greetings to all the students, all the professors, researchers, friends, family. It is a very important annual meeting of the Industrial Physics Program. I want to thank and congratulate particularly the Department of Electrical Engineering, Electrical and Computer Engineering of our institution for having kept alive and kicking year after year consistently these type of activities, particularly through the Industrial Affiliates Program. Today, I have to tell you that today is a very busy day for undergraduate research here on campus. Just this morning, I was giving the welcome to a very similar activity to this one, but in the social sciences department. The students there are also presenting their undergraduate research projects. After this meeting, I have to go to another one in which the arts and humanities students are presenting their undergraduate projects too. And also this morning, I had to congratulate all the students that are being inducted into the honor roll of the civil engineering department. So for me, this is a very happy day, a day in which we are presenting and celebrating the achievements, in particular, of our undergraduate students. I want to express my appreciation to industry, in particular. See them here. I think the secret of the industrial affiliates program is particularly that the affiliates. Your contributions are very well appreciated. As you can see, these projects to me are fascinating. These are real engineering projects in which students are solving real life situations using what they know and what they don't know, they find out. That's the beauty of this. You have to learn that you don't know everything. So basically, you should know. There are things that you have to figure out, look it up, learn new things. And it was very interesting, the question that Dr. Jimenez gave to the students. You can have the most wonderful idea, the solution to all our problems, but the reality is that the devil is in the details. And I love the answer of the students because that's particularly what we saw here. So again, thank you very much. Congratulations to the students. Just a few numbers. So you know the scale of things that we are doing here today. And I thank Dr. Torres, the advisor of the Industrial Affiliates Program. for giving them to me. This year, we have a total of 24 projects. 24. That's wonderful. That's excellent. We have a total of 13 mentors. Mentors are fundamental on making these ideas, these projects a reality. So mentors, faculty members, anyone who is helping these students, I thank you very much. Your contribution is also fundamental for the success of these projects. And we have a total of 138 undergraduate students participating this year in the Industrial Affiliates Program. And we have 21 who are women engineers to be. And I'm very happy to hear that. Again, congratulations to all. Thank you very much to industry. Thank you very much to the faculty mentors. And congratulations to all the students participating. Thank you very much.
Thank you for joining us. At the moment in the agenda, we are a little bit ahead, but we can go ahead and take a break. There is some refreshment next room. You can go either through that door, or you can go outside. In the next room, the study room 244. So let's regroup in 20 minutes or so for the next presentation. Thank you.
The students leave their stuff here?
Yeah, you can leave there. Hello. Feel free to leave your stuff in the room. If you want to.
José. Le toca, después de 10 pisos, no sé el número.
No lo vi, pero estaba raro que no llegara nadie de noche.
Ah, no, sí. Casi todo el mundo parece que lo están viendo live.
Vi que hay 2 o 3 contados así.
Ah, ok.
De hecho, que iba a atender ahora, pero tengo que ponerle
Está bien, no te preocupes. Parece que está súper ahí. Miguel se fue. Vamos a comer.
Déjame buscarlo. ¿Los tuyos también están allá? ¿Los tuyos están allá? Los que vinieron conmigo ahora, esperen aquí un segundo que les encuentre el spot donde van a sacar la foto y nos vamos a sacar la foto y después entran otra vez. Gracias, después puedes comer. Ya lo tiene. Los muchachos, síganme un segundo. Cuando él acabe, pues lo mando a tomar café.
Sí, algo que tome café y
Vayan
lo
y tomen
llamamos
café.
entonces para tomar
Ahí se busca los muchachos.
Excelente, Raúl. Te felicito. Perdona que estás curado, porque las presentaciones. Sí, sí, del último minuto.
Adelante, estudiante. Yo estoy igual, estoy brincando de aquí para allá de toda la mañana.
Pues lo que le van a decir, es que vamos a tomar que le contestará a otros podemos, por la que representa, volver al También, pero si lo quieren hacer así, pero díganle que tenemos una posibilidad de poner acá, pero cualquier persona que lo puede ver y que está basada en el qué bonito, qué bonito. Yo ya le mandé un código que tiene los estudiantes de desarrollo y ahí se va a recibe también los 4, 5, 6.
Ayer estuve
Hay diferentes filtros que se utilizan. Puedes escoger. Sí, sí, vale, pues yo voy a tomar un café porque ya me viene el desayuno. ¿De qué les pasa?
Yeah, by the way, also, sí, porque Kovacs es gran parte de la experiencia, es una de ellas. Literalmente, eso es lo que está hablando ahorita. Parece que me va a botar. Activate fallback functions, which are essentially Python declarators, which essentially are
Ayer, eso fue ayer. Sí, gracias. Jiménez. Así que no voy a mencionar cuándo yo me gradué. Eso sí no lo pregunto. Eso sí no lo pregunto. Uno más y para su casa. Exactamente. No tengo presupuesto para
Pero me habías dicho ustedes molestan que yo no hay que usar si no claro que
Sí, sí, fue ayer también. En esta época como que hay un poquito de... Y hoy como que se estoy allí y estoy resolviendo un problema de optimización. Bueno, deja ver cómo... Bueno, por eso yo puse a las 11 el otro, a ver si puedo... Obviamente, pues, participar.
Ah, no,
El 120. Es eso, perdón.
Está más cerca. Eso es inicio, primero se expresa allá. Y ahora pues
Exacto.
No te preocupes, profesor, que la lleve.
siempre trabajan grabados. Sí, seguro. Sí tenemos, pero no tenemos esa penetración, ¿verdad?
Don Carlos es excelente para esto de organizar los grupos.
¿Comiste algo? ¿Sí? Ah, pero hay café, hay de todo, sino que oye, hay agua también. ¿Tienes agua? ¿Qué vas a esperar? ¿Terminar esto para ir? ¿No tienes hambre ahora? Hola, hola, mucho gusto, encantada. Respiren hondo. Sí, puedes llevar el iPad. Acuérdate de tratar de no leer. ¿Sí? Pero, ¿sabes? Puedes mirar y volver a hablar. No hay problema con eso. Déjame ir a hablar con Manolo, a ver cómo se funciona.
Mientras más se acerca el tiempo, más náuseas siento ahorita, si quieres me vino. Ya, te están peor. Pero estamos preparados.
Those triggers, you sit there, they basically and they are responsible to manage how the app will sort of react. Hence the reason why it's yeah, as always.
Hay que ver cómo es. Si es mejor realmente o cómo termina siendo
Si no lo ves, eso que se esconde. Tienes que decirlo cada rato.
Es precario.
That would be a great trip, not gonna lie. So, getting low battery now. Getting low battery.
Protocolario en el almuerzo.
That's the issue I have.
Todo está previsto, todo se cree. ¿Y para qué tú crees, que yo estoy aquí? Conociendo, ya tú estás planeando tu escapada. Mira, entonces, justo empezando. Hay que negociar, con él hay que negociar. Ya que molestiente, ¿cuánto punto de bueno me va a hacer? Si te quedaste hasta el final, tuviste lo que decía la experiencia, ¿verdad? Por ejemplo, pero que no firmó antes, que acá tiene un número antes, tú te das cuenta que él está aquí. Hay gente que escribió a las 7. Sí, pero hay gente que escribió a las 7 de la no, pero yo le estoy hubo estudiantes que fueron a la presentación al round table de ICRL y al de la CIDRA. Se ponen una foto. Yo se lo había dicho a Adriana Luna, le dije a Adriana, y lo puse en el chat que está Manolo, está Pablo. Tú puedes llevar a cabrón chico. Yo cuando llegué, y lo que ven por favor. Empezó a hablar y yo decía, tanta instrucción, ¿cómo presentar? Ay, Dios mío.
No tan problemático.
Aunque la mano en el estómago. No, tú verás, todo va a estar bien. Cierra los ojos. Cuando hagas eso, cierra los ojos, ponte las manos en el estómago. Ahora cierra los ojos, echa la cabeza hacia atrás, dejando como por un momento. Te llamó la gente de allá, Raúl. Te digo que vamos a empezar. ¿Sí?
Yo la vista que empezábamos a decir.
Le doy break.
No, mira quién está ahí.
Buenos días.
En el grupo.
Next, our next presentation is Brian Figueroa, Angel Garcia, Jim Pagan, Jose Quiñones, and Rose Sanchez, single event effect data post processing GUI. Remember that the antenna has to be pointed towards the public when you speak.
Good afternoon, everyone. My name is Rose Sanchez, and alongside my colleagues, Brian Figueroa, Angel Garcia, Jan Pagan, and Jose Quiñones, we will be presenting to you our project that we've worked along this summer, Single Event Effects, Data Post-Processing Custom User Interface. We will be talking to you throughout this presentation about our motivation to design this app. We'll go a little bit into what single event effects are, a background. We will then go into a few challenges and the progress thus far, as well as a few conclusions, and finishing with references and opening for questions. So our motivation for this custom UI is that the company is experiencing a large overhead with the commercial tools that they're using right now for the use case of this particular division. So our aim is to reduce this overhead by reducing loading time, startup time, and plotting time. And to increase the user friendliness of the current standalone device, it will be the user will have a user-friendly interface where the user will be able to upload and project the data as well as plot it and export it.
So what are single event effects? These are measurable effect to circuits due to an ion strike. Some of these errors can be soft errors or hard errors. An example of soft errors would be single event upsets and single event transients, while the hard errors would be single event latch up. The challenges that we encountered are handling big data, since they had many data points that we had to consider when plotting this amount of data. Optimizing the functions such as the nested loops and multi-thread functions, of course, debugging and multi-user programming.
As part of the front-end team, we started first with the design. This is the design Texas gave us. This is the requirements they wanted. They wanted a program that could plot multiple graphs, it could read TMS files, multi-input handling, filtering window types, and was capable of saving the report of the data. As you can see, it's a pretty basic GUI. It does what's needed. So we made this design. As you can see, we have more plot spaces. We can choose the scope signal, the offset, and the values if you want to see it in seconds, milliseconds of time. We made the option to choose filter type or window type, and the normalized data would take out the noise in the graph and basically make it look cleaner. Yeah, here you can choose the plot you want to see your data in. This is the front end, the GUI, how it looked. After we programmed, we used Dash to create this GUI. As you can see with Dash, we made the drop downs. Like I said earlier, we could choose the signals, the scopes, and here we can upload the data, save the report files, normalize the data, which I said earlier would clean the graph and how it would look. And we have our different tabs with our different functions.
default settings, we have the filter type, the scope user, the signal user, the offset user, the filter data, and the normalized data. So these defaults are interchangeable and is depending of the user if they need to change something. For example, normalize the data, choose a different filter to cancel the noise. The callbacks are, as you may know,
Convert LabVIEW files to Pandas data frame, and we use Jupyter notebooks to basically try to break a big problem into something a bit more smaller. And yeah, we basically basically learn a lot. We actually learned about single event effects. We learn a lot about big data, how we actually use pandas specifically to sort of manage this. Some of us did not know much about Python. I knew Python before, but I know a lot more, so kind of happy for that. We learn about other technologies like Plotly, NumPy, which is like the precursor of sorts for pandas. We also learn different kind of techniques. We learn filter techniques. We actually learn Tkinter a bit. This was actually pretty interesting, since Dash is actually a multi-thread program, and Tkinter is a single multi-thread program. So we were able to somehow take these very two different, basically frameworks, and make them work together, which was actually pretty cool. And for at the moment, we actually have, as my classmates showed, we have a functional design. You can actually see it later on lunch break. Actually, it's on one of our computers. We got a few callbacks. Uploading one, the plotting one specifically. It has a small bug that we're actually fixing. But it also does the processing, which we actually verified and successfully works. So yeah, pretty excited.
For our future work, we are going to be implementing a function to display the different quantities of graphs depending on what the user chooses, in addition to a configuration menu, as well as doing a transition from what the app currently is, which is a web server, to a standalone application, and eliminate nested loops for further optimization and speed up of data plotting for our use case. Here the figure kind of shows what we were trying to do for displaying the desired graphs, number of graphs per screen. So these are our references that we use to develop this web application. So, and for questions, you can contact us at the following emails in case you have any more questions regarding. And now we open up for questions.
I have a question. You were hired to minimize the time of upload. What is the time of upload when compared to the uploading time of the tool that we're using?
Oh, that is a great question. For the uploading time, the application, the commercial application, the commercial tool that they're using right now has a loading time of 25 seconds per offsets, which is quite slow when you're trying to do this many times over. What our current application, custom application can do is around less than 1 second per file read.
I'd like to add that the data that we receive, it has over about 10,000 amount of data points. So this scales up quickly, and it keeps on adding much more time than it's desired.
So question, in the beginning, you said about three failure mechanism. One was latch up. Can you explain that, what happens or how it happens?
Okay, so these are devices that are used in space. When an ion, a particle, hits the circuit, it destroys the circuit, creating what would be a latch-up, which is a hard error, and it's basically drawing more current from the transistor, creating a parasitic device. I'm not sure if that answers your question. Yes.
Yeah. Is your There are two questions actually. You mentioned that your application is running through a web server. Right? What optimization tools are you using? Are you using, and is your application open to the public or is it just locally hosted?
Well, at the moment, yeah, Ultra's Dash is essentially web-based. We actually have it on a local host, since that's kind of the whole idea. And in terms of optimizations, well, specifically the upload part, that was actually one of the biggest challenges. So we actually had to try to experiment. We first tried to utilize the full Dash uploader. Unfortunately, that framework in particular had a lot of limits, so we actually had to go and search for third parties. We found one that was able that allowed us to actually even upload 4 GB. However, it was surprisingly slow, so we decided to go back to Tkinter. And in Tkinter, we were actually able to get it like almost instantly, essentially. It was kind of a challenge though, because, well, again, you got a multi-thread application with one thread application. So, trying to get both working together is kind of hard, but we were able to get it.
So you mentioned that for future works you wanted to eliminate nested loops, and my question is, have you thought of a way or some kind of way to eliminate those nested loops? Maybe of a research paper based on the algorithm or a technique.
Well, it's actually a bit more simpler. The idea is that instead of using nested loops, we actually would use matrices instead. Basically, using vectors, matrices, all the computations that NumPy and pandas often do under the ground, under like the background, since those actually are much faster, and they actually resemble a lot of the way MATLAB works.
So you have a question there. My question is, what was the hardest part of it, and where did you guys struggle the most, and how did you get past it?
Yeah. So for me, one of the hardest parts, I had to learn Python from the ground up, and also understanding the complex source code that we got, and then try to make the GUI work with what Angel said, that using Tinker, single thread with a multi-thread, and mixing those things together, it was a bit of a challenge. And afterwards, I think I can speak to all of us that we learn about how everything works and how to interconnect different programs for other developers with us and what we develop. And that's a really big area of, I don't know if you.
One other thing I would like to add is at first, one of the challenges we faced was that we couldn't use GitHub. If you don't know, GitHub is a platform where you can share your code with others and program the same code at the same time or alter one code. The problem with that was that with Texas, we couldn't use GitHub because of privacy issues, and we were forced to use and compare our codes using different computers that was a challenge for us because we had to go line by line, compare what did you do, what have you done, and try to incorporate that one into one laptop. And we had a lot of issues with that because sometimes code has 1,000 lines and you can skip one line and the code won't run. And so that was a big challenge that we had to face when connecting all the versions.
Thank you.
Any more questions?
Following up from the optimization question, I was still wondering about if the idea was to use Python libraries like Panda or NumPy, or to implement them by yourself to your needs.
Doing it on ourselves is honestly kind of complicated, and on Python is not really ideal, considering that it's not a file language. So it's much lower. And NumPy and Pandas, by the way, they actually are essentially wrappers if you think about it, because they run either C++, code, C code. I believe they even run Fortran code, if I'm not mistaken. So any optimization that you might think, chances are it's already on those libraries. We just gotta use it.
That will be the last question because we have to keep up with the agenda. Thank you very much.
Thank you.
Our next presentation is design and implementation of a solar panel emulator as experimental educational platform for microgrid research at UPRM.
Morning. We are presenting our solar panel emulator project, which is also our capstone project. Our members include Francisco Rodriguez, Andre Alameda, and I am Gustavo Blanco. We are working with Professor Dr. Adriana Luna and Professor Erika Ponte, who is our capstone advisor. Briefly, our solar panel emulator is a solar panel emulator is a DC source which is capable of modeling any PV characteristic curve, which include voltage versus current, voltage versus power, etc. Using a solar panel emulator versus a real solar panel allows you to choose the values of irradiance and temperature, which if you're using a real solar panel, you are basically at the mercy of nature. If it's cloudy one day, you might not be able to get the data that you want. So another good thing about a solar panel emulator is that you can model any solar panel, not just one. You can model any if you have the data sheet. It's important to mention that this project is for use in the Renewable Energy Center for renewable energy research at the Sustainable Energy Center. I'm going to talk to you about our system now, specifically. Our system consists of a DC source with a fixed voltage connected to a DC to DC converter, which is capable of manipulating the voltage and current at the output, depending on the duty cycle. We'll be using as our load a bidirectional voltage source, which can function as a battery. And whichever voltage we set at the battery is where we're going to be, the operating point where we're going to be in the characteristic curve of the panel. Finally, our microcontroller is going to read the output signals from the load and control a MOSFET in order to reach the current that we want. There are already PV emulators in the market. The problem is that their high cost is due to them providing a very high output power. For example, Chroma and EchoSense provide a PV emulator for more than $7,000, which is out of our budget, but it's for 1,000 to 2,000 watts when our project is set to a maximum of 200 watts. So it's understandable the difference in price. It's also worthy to note that some companies never even answered our quote request, so it's a little hard to find PV emulators in the market right now. Now I'm going to leave you with Francis to talk about the objectives.
As part of our project, it's a part of a capstone, so we require precise objectives. So we divided them into 4 categories. We did, can you hear me? Okay. We divided them in 4 categories: design, construction, evaluation and analysis, and preliminary testing. First, the design of the solar emulator was based on simulation parameters and the equations of the solar panels of Dr. Eduardo Ortiz. The switching frequencies and max output power of 200 watts were assigned by the client's requirement. For the construction of the solar panel, we divided them into 2 parts: the construction of the prototype and the construction of the PCB. In which the max physical dimensions were assigned by the clients and are meant to be not bigger than 24 by 36 inches. There's going to be an evaluation of the 3 design alternatives that will be analyzed based on efficiency, cost effectiveness, life cycle, failure rate, and strengths and weaknesses based on SWOT method. Finally, we are going to test voltages and current that by requirement should be 1% or less of right or ripple. The efficiency should be 90% or more than, and the physical system design should operate below 90 degrees Celsius. For the project, we selected the RSP 200D solar panel of 200 watts, with all the parameters used being presented. Now with Andres for the design alternatives.
Good morning. I will be presenting you the 3 design alternatives and the evaluation method. Our first alternative is the buck converter that works by stepping down the initial voltage and stepping up the output current. Stepping down the output voltage and stepping down the output current. Here we can see the layout of our simulation. On the left side, in part A, we can see the DC source input on the green color. On the center, we can see the schematic of the buck converter, and the right side, the load in orange. On the center, we have our microcontroller, and it's composed by Dr. Eduardo Ortiz PV model. Now, in the part C, we can see the scopes that are separated and organized to see the behavior of the simulation. Here we can see the components and the values calculated of each component by the simulation. Here we can see the graphics. On the left side, we have the PV microcontroller graphic behavior. We have optimal values of 22.6 voltage and 8.85 amps. That is the optimal point of RSP 200D panel. On the right side, we can see the behavior of the load, and if you look at it, you can see that they are very similar at the optimal point. We can see here the 22.6 and the 22.6 here, and you can see the behavior. Now, as our second alternative, we have the buck boost that works by stepping up and stepping down. You can do it by the goals you have as a designer. The downside of this is that the buck boost can invert the output of the voltage and the current. Here, you can see the layout is pretty similar like as the buck, and you can see the left side the DC source input the buck boost schematic, and the right side, the load. Here we have again our microcontroller, and you see we have the scopes. Here are the components and the calculated values. Now we're seeing the graphics. The PV microcontroller is working at the optimal point at 22.6. The PV current is working at 8.85, and the power is working at 200 watts. You can see the load is working similarly. Now, as our last alternative, we have the semi converter that works similarly to the buck boost, but it has the benefit that it doesn't inverse the output of the voltage and the current. Here is the layout, similar to the buck boost and the buck converter, but you can see here that we have 2 inductors and 2 capacitors. That's the difference, the main difference on the design of this converter. We can see here the behavior of the graphics. We can observe the ripple. We have this ripple because this converter works with higher frequencies than we use on this design. We use these frequencies because it was a requirement by the client of the project. We are going to see now how it's working with the optimal frequency of this converter. You can see here with 500 Hertz, the converter works in an optimal point. Now finally, we are seeing our evaluation process that we use a couple methods here. We need to do numerical methods to have an objective selection. Here we're seeing efficiency, cost effectiveness, life cycle analysis, SWOT analysis strength, SWOT analysis weaknesses, failure rate, and knowledge availability. For the goal of our project, the best alternative was the buck converter. Now I will leave you with Gustavo.
After choosing our design, we started to perfect our parameters for the buck converter and our control system. We realized that our inductance and capacitor values were too high, so we increased the switching frequency a little bit from 20 kilohertz to 50 kilohertz. At low voltages, we also encountered a problem where ripple and accuracy were too, the ripple was too high and the accuracy wasn't as great, so our solution was to decrease the sampling time from 1 microsecond to 0.1 microsecond. The PI controller was changed from discrete time to continuous time because we found it easier to understand the tuning, as well as we added a clamping as the anti-wind-up method to eliminate the error that builds up in the integrator. As mentioned earlier, we found new values for inductance, capacitance, as well as our Kp and Ki constants. Here we have our latest results in a summary format. Presented are the optimal short circuit and open circuit values. Clearly, these are not truly short circuit and open circuit because the buck converter just limits us. We can't reach those values, but those are as close as we can get. And aside from that, the simulation appears to be a great step in progress for the project due to the values correlating so well with the solar panel's expected behavior. I will leave you with Francis to speak about the prototype.
We constructed the design of the prototype with a commercial buck converter. In the testing process, we used a lower power of 10 watts or to up to 50 watts as a proof of concept of the simulation design. We realized during the testing of the converter that the duty cycle was controlled by voltage with a potentiometer that we removed in order to control it with a supply source as acting as a duty cycle. Due to limitations of the converter, we changed the converter and connected it to the controller. We achieved readings of voltages and currents read as voltages. Yet the current sensor used was bigger than the current measures and didn't got the readings of the current precisely. This affected the project because we couldn't make it a closed loop with the PI controller.
therefore only getting readings in an open loop. At the same time, the construction of the prototype, we designed the PCB schematics of the solar emulator of 200 watts. It has the input connections, a buck converter, current sensor, and voltage divider is a voltage sensor. As a result, we had a 2-dimension and 3-dimension PCB with dimension by 6 by 4 inches. The components used were selected based on the experience of the prototype construction and the simulation process. There are some references used in our project, and thank you for the opportunity.
Any questions?
So when you were considering the buck, the septic, the buck boost, you're making some trade-offs, right? What were the trade-offs that you were looking for?
We were looking for optimal efficiency. We were looking for control system. That's for the evaluation methods. We have the buck converter and the buck boost converter functioning well. So in that case, we actually was looking for a way to control the whole project. That's the part. Yes. Follow-up question from Miguel, though. If you go to slide where you choose why you choose the buck converter, did you weighted each parameter equally to choose buck converter, or
No, they're weighted, the percentage is the weight on the left.
just based? And how did you decide what weight more versus less?
Well, based on the goal of our project, we have a budget, and we were seeing what converter and simulation works best with our limitations, parameter limitations. So analyzing the efficiency, the cost effectiveness, and the failure rate, we saw that the step converter was really good at higher frequencies, but we can use it because of our 20 kHz frequency. So that was a problem. So then we have the buck and the buck boost. And when we are seeing our milestones, the goal was implemented in a physical prototype. And if you work with the buck boost, the design of the buck boost physical, it inverts the output voltage and the output current. And the efficiency in that is low, and it takes a lot of time, and it takes a lot of knowledge in design to not burn or harm any microcontroller or any equipment. So that's why we weighed the efficiency, the cost effectiveness, and the failure rate, because the buck boost was really good, and we can design we can invert the output, but the failure rate is really high. So at the end, we choose the buck as the best option for our project. Thank you for the attention.
Thank you very much. I apologize for the person viewing the YouTube channel because we are having trouble with the camera. For some reason the preset were off and we're jumping around in the live stream. Next presentation will be drones, university showcase. These are three teams presenting as one presentation.
morning. We'll be presenting the Unmanned Aircraft System University Innovation Showcase. That was a rating competition that we did beside with 3 groups of the university. I will be presenting my group, the Spear Team. We have Brian Diaz, Onel Lugo, Fernando Sierra, Dan Montes, and myself, Xavier Nieves.
Good morning, my name is Ale Pagan. I'm going to present the other team, which is the Collins Aerospace team. So, John Santiago, Juan Iranzo, and Ale Pagan.
My name is Amado Ibero. I'm representing the Raytheon team. I'm basically myself for today, but we are 5 members in the team. So, for introduction, the purpose of the US Unmanned Aerial System is to do basically for the students to be creative, innovative, and to solve the problem solving of the world for the company, in this case, Raytheon. Next slide, please. So the objective of this competition are built within showcase. So basically each showcase means a mission we have to complete. And the first showcase is to fly the drone autonomously from the start point to the end point. The second showcase is a camera to detect the ARC code and also detect if it's a friendly or a foe. A foe means an enemy. So basically you have to detect if it's a friend or an enemy. And then the third showcase is to ground the ground vehicle to run autonomously for about 150 yards and end in the ending line and exactly at that point. So basically it runs autonomously and it ends autonomously in the end point. And then the fourth showcase is for the UAV, which is basically the ground vehicle attached with the laser tag receiver. So the laser tag gun for about 75 yards. So basically the ground vehicle run about 75 yards, and then with the laser tag, when you shoot it, you must stop immediately autonomously also. So you must run autonomously 75 yards and then stop when you shoot it. And then the fifth showcase, which is the last one, will be the UAV, which is the drone with the laser tag receiver, to detect the ARC code and also to detect if it's a friendly or a foe. Basically, detect if it's a friend or an enemy.
The UGV, what does it does, how does it work, what can improve future plans? Every car in the competition representing each team, it was a target that the drone had to fly around, target it, identify it, if it was an enemy or if it was a friend. If it was a friend, ignore it, go to the next one. If it was an enemy, shoot it, make it stop. And when all the lands are clear, the drone would just go safe. The function of it was just to run around any showcase, go basically up front and make it stop whenever we want it to stop.
Part of the showcase, we had to do an autonomous drone. We used at least my team used a Taro T960. That was a hexcopter drone. It was capable of multiple things, but at least we integrated it with an Ardu pilot system that made it completely autonomous from start to finish. It was autonomous from start to finish. It used a GPS system to navigate and know where it went in coordinates. At least that was the system we used. It depends on PID calibration systems in case of failsafe or to identify anything, so if it would fix itself or self-leveling, it would use this PID calibration system so it wouldn't fail.
So for the UAV, the type of UAV we used, that was the Taro 960, as the teammate said. We use this because it is a hexacopter. How you can see, but on the contrary, the quadcopter doesn't holds up less wind than the hexacopter. This drone has a payload of 6 kilograms, so we could meet our requirements for modifications. We did
We did a case for the battery, so it could be in the center of mass, as a case with for the autopilot and the Raspberry Pi. The case of the battery act as a gimbal mount and a laser mount. The gimbal we did it 3D printed to meet our requirements because the gimbal we had didn't was a 3-axis and didn't meet with our requirements, so we did a 2-axis that was the one that we needed. And for the protection, the propeller protection was a requirement for the competition. We did it 3D printed, as you can see, and we use a bucket of Home Depot.
For the Collins Aerospace team, we use a Floyd D camera, which is specialized for video vision image processing, and that camera, not in the host being the computer. So what does it use? Is also the camera and OpenCV, which is a library that is in various languages. We use it mostly on Python, and we can see the images there. We can recognize between enemy and friend. Besides that, what we can improve? Both teams have problems between looking down in the field, because if we look down in the field directly at the sunlight, the light reflects from the ground, so the camera does not see. It's not able to see. So the way to fix that would be to do focal lens, and the zoom lens is because we can see from far, but not that far, which means that if we want to cover more ground, which means that the ground is up in the air and the cars are all spread around, then we need a more zoom that we can use. And for future plans, we wanted to decrement the time it takes to interpret the code, which means to switch from Python to C++, meaning that it's faster and is less heavy on the hardware.
How does it work? Basically, using when you detect your code, a marker, we centralize the camera. So through the Raspberry Pi, we send a signal, so it will move the servers in the X and Y direction. And
to control the movement of the server, we use pin class from GPO 0 library class library. This library provides us with an easy to use interface to interact with GPO pins and of Raspberry Pi and control devices.
To integrate the camera in her project, we used a rocker marker detection. In her case, we detect the position of the marker, and the marker coordinates in the image captured by the camera, and adjust the X and Y angle of the servos to marker the image until you reach the square representing the center.
it's the video how it's work.
We're live.
Oh, impossible. Okay, slight malfunction.
You can see then when you detect it moves, so it's centralized in the in the center of the video. So we use a reference point, in this case, of the center of the camera. So it will stay on the Aruco marker. And what can be improved? More ratios, so if we can implement more optimization and the unify of the computer and the system.
Let's just skip this.
So this is different, so it won't do nothing different. Only the targets, enemy target.
Any questions, any doubts about the system? Feel free to ask. Ask away. Ask away.
Can you guys go over the major challenges you face and what would you do differently next time to overcome those challenges?
The major challenges we had was exactly the sun. The sun affects a lot the camera function, but the functionality of the camera, since it's hitting directly, so it looks all white. At least in the video you saw, we had to put a polar filter of 256, and it was still as white so it affects the detection of the Ruko marker because it's white and black. So and the reflection wouldn't let it target it. So that's why we had to put people to cover and shadow the Aruco so the camera could see it. And any modification would be try to put at least some type of polar filter or anti-glare on the Aruco markers so it wouldn't affect that much when the sun is hitting on it, and put a stronger polar filter on the camera so it wouldn't be affected that much. And obviously a better camera because our camera also had it was a webcam, a Logitech webcam, really cheap camera, so it took a long time to focus once it went in the air. It took a long time to focus, and when it was flying, since both systems aren't fully operating together, you're operating the Raspberry Pi was searching and controlling the gimbal, the RD Pilot was just flying. We can merge the systems together so to tell them, okay, if you detect it, follow it, and then shoot it, and then continue the mission. We can implement that. So those would be future works, future improvements that we would have to do to the system to make it more reliable.
Sure.
Thank you. Answer the question?
Yes.
I also wanted to answer that question. At least for the Collins Aerospace team, I think that the most challenging thing that we had was that we were working with different kind of hardware that was not actually compatible itself. It was not just plug and play. So really had to go into the files and modify these files and just get the permission we wanted to, just to make it compatible. Like for example, we were using a PSR controller for the UGV and a Raspberry Pi, and the way we were communicating with it was from the pins from the Raspberry Pi to the telemetry 2 from the PSR. And that worked perfectly, but at some point it didn't. And that's the part where we got stuck because we did not know if it's a hardware or software problem. And to eliminate this problem, I would prefer to next time we plan our design, make sure that these parts work as well as in plug in and play, not try to make do with the hardware.
In the races, it will be that the ground vehicle, basically, we had to do a lot of, well, let's say we didn't do a lot of tests with the ground vehicle, so when we actually did it in the competition, there's a lot of holes in there, so it was a lot difficult to make it sure that the ground vehicle will go to the finish line autonomously. So let's say that we have to do a lot of tests, like basically do a lot of tests and make sure it's most to the deal area of the competition. So make sure it works exactly as it is in the competition.
Awesome, thank you.
Any other questions?
We need to move on.
Thank you. Have a great day.
Good job.
Well, if you're interested in this research or this project, the competition is on for the next year. So if you're interested, talk to your friends and we can make another team. Our next presentation is TPL, clusterization for low current devices.
Good morning. This is a presentation on low current transmission, PLP characterization for low current devices with research partners, that it is Collazo, Ian Santiago, Eugenio Lopez, and myself, Anthony Crespo, PI liaison Pedro Escalona, and our mentor, Gladys Ducodre. The outline that we'll be presenting today includes transmission line post, motivation challenges, and simulations. The transmission line is used to test a device's electrostatic discharge and behavior by observing its voltage and current oscillatory waveforms. It is originally used for high power devices or high current devices, and its ranges, these are its typical ranges, and its benefits include that it dissipates energy to avoid destruction and its thermostable characteristics. The challenges that were faced is that the original TLP is used for high current devices and we want to implement it for low current devices. For this, we need to add a device that minimally alters the current in the system. Possible solutions for this would be to include a 50 ohm resistance and measure the voltage across it, or add a high-speed dynamic sensor with an impedance of 50 ohms. The tools used in the project, this is the simulation, the transistors used, and the instruments used in the lab.
Now I'm going to talk about the simulation that were realized to test the TLP. The first simulation that we realized was to characterize a lossy transmission line so we can study the behavior on reflected signals and delay on the signals. And we can see in the graph here, we have the input signal as shown in pink. We have the input to the transmission line in green, and we can see a slight delay between both of them, and the output of the lossy transmission line in red. We can see more delay between each signal. Then we change the transmission line instead of lossy. We use an RG58 gauge cable. The RG58 gauge cable was implemented to a BGT transistor. We measure the input and the output voltage across the line. As we can see in the graph of voltage here, in blue is the input signal, the yellow is the output signal passing through the line. We can see a little rebound in the output of the signal and a small delay between each of them. Then we can see on the collector and the emitter of the transistor, we can see that current entering has a slight rebound too, a consequence of the RG58 gauge cable. Then we proceed to make the parametric sweep on the length of the cable. The length varies from 1 meter to 10 meters. We can appreciate the longer the line, the slower the delay between each signal. We can appreciate it in the voltage and current graph in here. There are the parameters that we use to characterize this circuit. Then, after making the simulations, we made physical implementations. We tried two physical implementations, one with the BGT transistor and one with a MOSFET transistor. In the BGT transistor, I give it a little offset so we can appreciate a little more. The delay is small, but we can appreciate a little more in this graph here. And in the MOSFET, we can appreciate approximately a 5 volts loss in the line because in the source of the transistor there's a 50 ohm resistor entering the source.
We did simulations with and without passive devices in order to be able to compare both of them. The first one we did was without the sensor to see the behavior of the currents and the voltages, and later take measurement of them. The simulation, then we did a simulation with the sensor. We put a 50 ohms resistor in the source of the power MOSFET in order to measure the voltage across it and the currents. That capacitor that is parallel to the resistor is simulating the oscilloscope that is measuring the currents and the voltages. Here we can see the graph of the currents and voltages in order of gate, drain, and source. The measurement that we took from that in the circuit without sensor, we took an average window between 0.44 microseconds to 0.46 microseconds. The voltage that we took from from the gate to source was 3.33 volts, and the voltage between the drain and the source was 3.12 volts. The currents in the drain and the source were the same, were 160 milliamps. And in the circuit with the sensor, we took an average window between 0.22 microseconds and 0.24 microseconds. The voltage in the gate to source and drain to source were the same as the circuit without the sensor. And the currents in this case in the drain and in the source were 174 milliamps, and the error found in this is 13 milliamps, which is it's not bad, but is a little big for what we want to send.
For our second proposed solution, we use simulations with active devices. This is a high-speed dynamic sensor. It originates from one of the IEEE published papers. This circuit consists of a current mirror with series cascoded MOSFETs. We're utilizing high-power MOSFETs because we want to characterize that ampere to milliamp as far as we can go. So we needed one that could be utilized with that higher amperage and not be burnt out. We varied the voltage and current between these ranges for the sensor and its input to see if it was working properly. And once we were done testing it initially, we began using TLP with it, with high amperage range. We characterized the circuit to work with a current offset and a DC offset. This is made so it's always on, and for it to work properly, it always has to be on. Our device under test here is a BJT, and in the first graph we can observe the current flowing out of our source and the current out of our transmission line. In the second graph we can see the current flowing in red flowing through our device under test, and the one in green represents the one coming out of our output for the sensor. We can see that the difference is negligible, and it stabilizes about the 1.6 amp range. Once we were done testing it with the higher amperage range, we lowered the parameters both for the transmission line pulse and for the sensor to see how it performed in lower ranges. You can see the voltage graph where the blue line is the initial pulse and the red one is our voltage at the end of the transmission line. The current in the second graph is the current flowing through our DUT, that in this case is a high power MOSFET, and we can see that it follows the current with the output for the sensor follows the current properly. We chose a segment of relative stability to test the error rate. The error rate we found was about 500 microamps. Key takeaways for this is that it would work for the amperage, ampere range, and milliamp, tens of milliamps. but once we get to that lower range, it loses accuracy. Concluding remarks, we can use active and passive devices to measure current in TLP, and with the high-speed dynamic current sensor, we can measure high currents to small currents with that small error rate. These are our references for our presentation. That would be all. I thank you for your attention.
So between the simulation and measurement, what is the major difference did you see and how did you resolve it?
Between the simulation and measurements for which specific sensor?
Either
one. For here, between the difference, we chose this initial method. We need to find a point of relative stability. This comes from the initial paper for transmission line pulse. That you need to find a point of stability, an averaging window, and then you use this graph. It's used to characterize circuits, usually by validation engineers.
I think he's asking you from the simulation, did you simulate it and actually tested those same transistors when you actually in the lab put them there? Did you use the same transistors, and if they were the same, how did you manage to subside the differences?
The emitted transistor is the same that we simulated in PSpice, but the MOSFET transistor that we tested in the lab is not the same. It has more or less the same specs, but it's not the same because we didn't have at the moment the same transistor that we were using in PSpice.
The high-speed dynamic current sensor is yet to be physically tested. It was tested more in simulations. Does anyone else have any questions?
Do you plan to do the testing on the bench and compare your models to that?
Yes, we're planning to implement the circuit at some point.
And do you have some idea of what will be acceptable from an error point of view?
I think the 500 microamps is a bit high, maybe lower it a bit. It can be the initial setup for the high-speed dynamic current sensor. It has another side, which is PNP, and we would try to implement that side to increase that accuracy.
Another question? Okay. Thank you for attention.
Thank you very much. Our next presentation will be developing tactile sensor using Hall effect sensor.
Escucha. Well, good morning. My name is Jose Martinez. This is my partner Jaime Rosario Escobar. And this is the project that we worked on. It's the development of a tactile sensor using a Hall effect sensor. Our advisor is Dr. Guillermo Serrano. Our liaison is Gabriel de la Cruz. And our sponsor is Texas Instruments. The Hall effect. What is the Hall effect? The Hall effect is a phenomenon in which a perpendicular applied magnetic field perpendicular to a conductor induces a voltage across the width of the conductor. Well, why does this happen? Well, the applied magnetic field since the electrons are moving inside of the conductor, the magnetic field results in a force that shifts the electrons to the sides of the conductor, resulting in negative charges on one side and positive charges on the other side. This results in an electric field and a voltage that we can measure. Well, how can we use this? Well, by varying the intensity of the magnetic field, we can vary the intensity of this induced Hall effect voltage. An immediate thought one can have is that, well, we can use a magnet, an electromagnet, or a permanent magnet to induce the voltage in the conductor. Then, this varying voltage can be used to control an external component that changes the position of the magnet in a way that simulates
compression. We want to design a tactile sensor for different applications like robotics, prosthetics, and the objectives of this research project were to select an appropriate magnet to characterize the Hall effect sensor that we were using and to test the sensor with the chosen magnet in different configurations, a threshold configuration and a negative feedback configuration.
Here we have the DR55 sensor, which is a linear Hall effect sensor manufactured by Texas Instruments. Here in blue, we can see the voltage equation relating to the magnetic field. And also we can see a graph of the output voltage related to the applied perpendicular magnetic field. We can see that when the south side of the magnet is pointed perpendicular to the sensor, the voltage increases until a voltage of approximately 5 volts, which is our VCC. And when the north side is pointed, it reduces to approximately 0 volts. The sensor comes with 4 different sensitivities, and here we can see a typical schematic of the application of the sensor. Magnet selection. When selecting the appropriate magnet for our application, we have to take into consideration the type, the shape, the dimensions, the resonance field, and the application range, which is a displacement of approximately 5 millimeters to 9 millimeters. Here in blue, we can see the magnetic field equation related to the distance for a cylinder and also a cube. Here we can see also the perpendicular vector field for the magnetic field for a cylinder and also a cubical magnet. Here we can see the magnet selection curve, some characteristics curve from 2 different magnets, a cylindrical and a cubic. Here in the cylindrical, we can see how it changes voltage in our desired displacement for 9 millimeters and also to 5 millimeters for different sensitivities. And also we can see the same for the cubic magnet. However, for the cubic magnet, there isn't enough voltage difference through those displacements. So we selected the cylindrical magnet due to seeing those effects of the applied voltage on that displacement, the output voltage. Our selected magnet has a diameter of 4 millimeters, a thickness of 1 millimeter, and a resonance field of approximately 1.425 Teslas. Here we can see our magnets compared to a penny size, and also we can see here how the magnetic field lines point outwards. Here we also have a sensor characterization curve. We have here our theoretical curve and also a measured curve for our desired magnet, and also we provided another characteristics curve for another magnet to see the differences. Here in the first one, we can see how it closely matches the theoretical graph, while the other, it doesn't follow it very much because we changed the radius, the different radius. Here is a test setup. We used a linear actuator to move the magnet towards the sensor, which was stationary. The setup was controlled with a motor driver and a microcontroller, and the actuator had a linear potentiometer that increased the voltage value when the distance increases. Here we have the feedback test. We further characterized the sensor. We completed 2 feedback tests. One was a binary operational test, which I'll put a position depending on the voltage. If the Hall effect sensor voltage was higher than the reference voltage, it'll automatically stop, while if it was lower, it will keep sending voltage to the motor. And also, we have the negative feedback test that the motor was driven by a difference between the reference voltage and also the Hall effect sensor.
We have some results. This graph allows us to see somewhat of the behavior of the motor, the movement over time. As we can see, the orange line is an example of a test that we did with a threshold configuration, and the blue line is an example of a test that we did with the feedback configuration. As we can see, the slope of the orange line is constant. That's because it was moving at a constant duty cycle. The slope for the blue line is not constant. It's steep at the beginning and then tapers off as it approaches a reference that we wanted it to stop at approximately the same reference. So as we can see, while the blue one is getting closer to the reference, the slope kind of tapers off, while the orange one just stops when it gets to the reference. Here we can see a histogram for the threshold configuration. As we can see, there is some variance in our collected data, But the outliers are they're very scarce. They're not very present. Most of the data we collected was very close to the accepted range that we wanted. Okay, this graph. This is a percent error versus the voltage reference for a constant duty cycle of 20%. On the x-axis, we have a voltage reference, which is the voltage that we set to the amp that we want to be at this voltage. We want the Hall sensor to move until we reach this voltage. The higher the voltage, the closer we are getting to the Hall effect sensor. As we can see, the higher the voltage, the closer we're getting, the more the error. However, the error is at 0.16%, which is a relatively small error even at its peak. This graph is the same graph, but for a feedback configuration. As we can see, the voltage reference increases, we're getting closer to the sensor, and the error increases as well. However, after testing, when we were doing these graphs, we noticed something, that the error in this configuration was significantly higher than the error in the other configuration. And we determined that it was because our test setup for these tests was not appropriate for what we did. There was some things that we could have done better. Our results in general is that the ideal permanent magnet geometry for our application is a cylindrical magnet. Operating the sensor with the first configuration showed a minimal error of 0.16% at its peak, and the sensor proved effective for our desired application. Future work would be to validate the negative feedback test results that we had doubts when we saw them. Apply a compressive medium between the sensor and the magnet to simulate the compression of a finger. Apply a setup for a prosthetic and/or a robotic hand, and use an electromagnet instead of a permanent magnet. These are our references. Any questions?
I have a question. So
yes,
you talked about doing your test at 20% duty cycle. Why 20% duty cycle? What was
the idea with a 20% duty cycle is that the linear actuator we were using had a limit to the minimum duty cycle that we could apply for it to start moving. Okay. And if we're going to use a constant speed, well, we need to find the lowest possible speed that it needs to start moving. And what we found, it was around 20%. Yes?
I didn't understand. You mentioned feedback and non-feedback. Why did you use feedback and what was different?
Okay, make clear. In both configurations, we use some type of feedback. With the threshold, we kept comparing to the voltage that the sensor was reading, but we didn't use it to control the speed. It was either high or low, a binary output. For the other configuration, what we did, we tried to use the difference between the reference and the voltage reading to control the speed of the motor. If the difference is higher, we want it to go faster. If the difference is smaller, we want it to go slower.
So which one worked better?
According to our test results, the binary operator. But we did realize that our test setup for the feedback was possibly not adequate.
Because I think he's taking control
Yes,
courses.
yes.
He should know better than
We have a possible explanation as to why it didn't work.
Yeah, a possible explanation of why it didn't work is because the Hall effect sensor provided a output voltage that is not very linear. Yeah. Yeah. Yeah, it's not very linear, so also the output voltage that it provides is also non-linear, so that's why we can see some error in the measurement. That's why the threshold voltage application worked better.
Has a difference of 0.1 volts and a reference of 4.6. Since the slope is much steeper, the difference in terms of distance moved and speed of the motor is going to affect the results a lot more the higher reference you have. So ideally, you need a lower gain as you're approaching a higher reference voltage.
Why weren't the test conditions optimal, and how are you going to fix it?
Yeah, that's it. We are gonna, in the future work, we're gonna apply different gains to different voltage references. Like Fernando said, there is not a one size fits all for our negative feedback test.
So in applying different gains, we hope that the error will be less. Any other questions?
Thank you. Our next presentation will be a smart carpool for our university. I think that is already implemented, okay? Some multidisciplinary research. And I got an invitation to carpooling. So I suppose that were the things. We're going to talk about it.
Hello, good morning. My name is Magdalena. I will be presenting our project, Smart Carpool System for the University of Puerto Rico, Mayagüez. I'm here with the rest of the team. We have Rumen, who works on the hardware, Misael on the back end, and Julie on the front end. What we want to do is work on a smart carpool mobile application that's designed for students from the University of Puerto Rico, Mayagüez, that has an optimized pairing system, which will create the carpool groups for the students based on their proximities and their similar arrival and departure times. We have a designated parking space that's on campus that has gate-controlled access so that students, as soon as they arrive to the university, they can head straight to the parking and we verify their location and then they can park. And this is all to reduce traffic congestion and also reduce the demand for the limited parking spaces we have on campus.
Okay, as we all know, there's a problem of demand and offer here at campus. And what we propose to solve this problem is to use a mobile application that create that pair optimal students creating smart carpool problems, carpool groups. Sorry. Now I will let you with my.
The project objectives are as follows. Our project aims to manage parking reservations with the use of our app and optimized pairing algorithm. UPRN students are paired based on proximity and desired arrival and departure times. Our project also aims to decrease the number of cars on the road and thereby decreasing the amount of traffic congestion inside and outside of campus.
For the methodology we used during the project was to explore the technologies available to implement the system we wanted. Also, we prepare and do we install the parking components and the apps on the Play Store, and also on the front end, on the front end, back end, and hardware, we tested that everything was working correctly. On the hardware, on the technologies we use on the hardware system, we used a Raspberry Pi microcomputer because it was economic and also it was very versatile for the project use. On the backend, we used Microsoft Azure web services with Flask for web application. It's a service that allows you to develop web applications using Python. Also on the front end, we use React Native that allows you to develop an app on multiple platforms at the same time without the need to do it one at a time. With the Expo tools, there are some tools for web to implement web services on apps.
Here we have some wireframes of how the application looks. On the left, we can see the start screen where users can log in and create an account. Then we have the home screen on the middle, and then on the right, we have the reservation screen where users put a date they want to go to the parking lot and their range of time, the arrival and departure. They also select if they can be the driver. After they put the capacity of their car, they input their pickup location. And then we can see just an overview of their rides, if they can see their status, if it's pending, if it's canceled or approved. And then they can just see the status of the parking lot. They can see the active hours and also the location of the parking
Now, for the results after a couple of months of hard work, we can say we're confident that the software component with the mathematical model can handle all the common scenarios that we identify. The hardware component of the system can also identify users that want to enter to the parking lot and allow access to them. The application was also launched to the Apple Store and Play Store. And finally, a web page for the application was also launched.
Our future work for the project includes the continuation of the testing of the program. Then when we finish the testing, we will implement the necessary changes to the application. And after all of the changes are made, we plan to fully launch the application to everyone on campus. Thank you. Any questions?
Yeah. What is the volume of the people that you're expecting your application to handle?
So as we know, for this to work, we need like a big group of people because we're working with carpools and we all want them to fill the parking lot. We hope that we have 30 parking spaces available. So if everyone goes like a 4 carpool, maybe 50 people will be a good volume to just test and measure the effectiveness.
It's a little bit of a follow-up to this question. What kind of testing are you doing to make sure that the system scales up to that user base?
So currently we're working on the beta testing. What we want to do right now is just see if the system works. We want to see if it optimized, the pairing is optimized. If someone cancels a ride, we can move them to another group. But for the testing, we just want to make sure that everything follows because for now they make reservations and they have a specific time that they have to arrive. And then if one person doesn't leave or arrives at a specific time, then it's like a domino effect. So basically for the testing, we just want to measure the system pairs correctly, if it connects to, we have a controlled access parking lot, so students, the parking arm has to open. So we just want to check that connection between the system and the hardware.
What's the feedback mechanism? How are you getting the data back to analyze it?
So for now, we're working on a very small testing group of volunteers. We have a form where they can just input their experience when they're testing with us. But we're measuring as soon as we working on the carpools. They're on the site. They tell us their feedback. We ask for it. They tell us, oh, something we figured out was that the application, if I go back to the wireframes, on certain screens that are bigger, you can see the bottom bar. So that's something they tell us when they have an issue.
Yeah, it is not expected, well, it's not desired to have problems on the field, but in case of anything happens, it's within the scope of the project to have some fail-safe to manage, for example, a cutoff of the electrical power, for example.
So as of now, Ruben can answer that better.
Yeah, the thing is that the mechanical arm has a solar power based system that means that the Raspberry Pi that does not ever turn off. And if the internet connection is lost, the Raspberry Pi reconnects when it's available again.
a legal one. Do you arrange any kind of insurance to cover students in carpooling? Like through the university, because this is a project.
Yes, so we are working, we want to meet with a legal team so that we can handle any type of legal accident. What we were working on, our strategy better was that students have to sign a consent form when they register to use the application. In case something happens or the driver has an accident or they don't arrive on time, then what we want to do, I believe, is that the student signs a consent form, so it wouldn't be our responsibility if a student on their way to the university has an accident. But we want to work and get advice from someone on a legal team.
Thank you. Thank you very much. We are going to take a break for lunch. We will be back at 1 o'clock. Please be on time at 1 o'clock. Maintain our schedule on time. Thank you.